In this video, we're going to talk about bonding of carbon. This is going to get us started in terms of understanding how carbons can connect together. And a couple key points we need to remember about carbon. Because carbon has 4 valence electrons, it's in group 4, and it needs to get to its octet to be, quote, satisfied, if you will. It needs to have 4 more electrons from somewhere. So what this means is that carbon likes to bond to 4 other things. And there's a couple different ways that carbon can do that. So let's look at the first case, bonding to 4 other atoms. So if we look at carbon and we draw a Lewis dot structure that has 4 valence electrons around carbon. Again, we need to make it so that carbon will have a total of 8 around its orbital shell. So let's just take a look at a very simple example. If we were to add hydrogens to this, so 4 hydrogens, each hydrogen is going to contain 1 electron. So if I were to bring 4 hydrogens with their single electrons near to the carbon, okay, what that will do, it will now give carbon a full octet. Okay, so there's 8 electrons in there. And hydrogen, because it's so small, it's actually satisfied with just 2 electrons. So this hydrogen now would be satisfied with its 2 electrons there. Okay, so this is the simple molecule called methane, CH4. And another way to represent this is to indicate that these 2 shared electrons are making a covalent bond. So we often will draw these out with single lines like this, where each line is representing 2 of these shared electrons. Okay, so that's bonding to 4 other atoms. Now this is a real simple example, but we could have it bonding to other things as well. Let's have it bonding to several other atoms. So let's put a carbon here again with our 4 valence electrons. And let's have it bond to some things other than hydrogens. Let's have it bond to an oxygen, for example. Okay, so oxygen being in group 6, it's going to have 6 valence electrons. And we have now an OH bond here. And notice if I bring this OH, the oxygen now currently has 1, 2, 3, 4, 5, 6, 7 electrons. But if I bring it now close to the carbon, that's going to now form a covalent bond, okay, thus giving oxygen a total of 8. So that's one example where we've got something else bound. Let's have a fluorine. Okay, so fluorine has 7 valence electrons. So if I bring if I bring it close to the carbon like this, that's now going to allow this carbon and fluorine to have a bond. Fluorine now has a total of 8, and I'm starting to now build up my octet around the carbon. Let's put a hydrogen over here. Okay, so there's now a bond. Okay, we have a bond here. And let's have it be bound to, let's say, a nitrogen. So nitrogen has 5 valence electrons. Okay, and I'm going to put 2 hydrogens on there. So there's a bond, and now notice that the nitrogen is going to have 8 total. I've now got a bond here. So I've now got 4 bonds coming out from the carbon, and notice that there's a total now of 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. And this carbon now has a full octet. Now if we were to draw this out using sort of the line methodology, this would just look like this. So the carbon has a bond to an OH, it's sharing 2 electrons. Here we would have a nitrogen that has 2 hydrogens attached to it. We would have a hydrogen over here, and then we would have fluorine. And I'm going ahead and putting in the lone pairs of electrons just so that you can kind of keep track of those. So this is an example of bonding to 4 other atoms. And again, the key here is that carbon's going to be forming what are called single bonds. So this is what's called a single bond. Okay, and a single bond is just two shared electrons forming a covalent bond. Continuing on with our discussion about bonding to four other atoms, let's just talk about the shape of a carbon when it bonds to four other things. So let me go back to this molecule that has the four hydrogens attached. This is the molecule called methane, one of the simplest, or the simplest alkane molecule. Now, as I've drawn it, it looks as if all of the atoms are in the plane of the board here. Well, it turns out that the shape is actually not flat and planar like that. And this goes back to something that you probably learned in your introductory chemistry, the Vesper theory, which basically deals with the shape of molecules based on the fact that each of these bonds and the attached hydrogen could be sort of considered a cloud of electrons. And we know that electrons are negatively charged. So if we put sort of negative charges out here, one of the consequences of there being four sort of areas of negative charge attached to this central carbon is it causes the shape of the bonds coming off the carbon to adopt a special shape. Another way to sort of represent this would be just to have a central dot, and imagine having little strings attached to negative charges. Now, I'm sure you all remember from introductory physics that like charges repel. So if I have a central point tethered to four different negative charges, and I sort of allow those to spread out as far apart as they can get, what this will do, it will adopt not a planar geometry, but a geometry that's called a tetrahedral geometry. So what this will do, it will look like this. So if I now envision my strings becoming very rigid and straight, I would have the negative charges at now the apexes of what's called a tetrahedron. And the bond angle of a tetrahedron is 109.5 degrees. So all of the bonds, or all of these negative charges, would be separated by this exact angle of 109.5. So carbon, when it's bonded to four other atoms, regardless of whether they're hydrogens or other carbons or nitrogens or whatever might be bonded, when there are single bonds like this, so four single bonds, this central carbon is going to adopt this tetrahedral shape. And the key number to remember with this is this 109.5 degree bond angle. So a molecule like methane has an overall shape called tetrahedral. And if you were to envision a tetrahedron, these points are now at the apexes, essentially, of a triangular pyramid. Okay, so it would have a side on three sides around and one on the bottom. But the points now, again, are at the apexes of this tetrahedral shape. All right, in this part of the video, let's take a look at what happens when carbon bonds to three other atoms instead of four. Last section, we looked at four. So when this happens, carbon is going to adopt a very different shape. Again, let's draw out our carbon with our four valence electrons. And let's now have it only bonding to three other things. Now, in order for this to happen, notice the way we typically draw a Lewis structure. We draw the electrons kind of surrounding the carbon symmetrically. What has to happen is that one of these electrons is going to be moved over here, and these two electrons are going to be moved here and here. So the easiest example to look at is this molecule. So here's now a bond to a hydrogen. There's a bond to a hydrogen. And now I'm going to make a carbon-carbon double bond. Okay, so what I've done here is I've made now my four bonds that are now going to be single bonds. Notice that's just two shared electrons. But here in the middle, something a little different is going on. Okay, so if I tally up my total number of electrons for each carbon, I'll circle them there. I've got 1, 2, 3, 4, 5, 6, 7, 8. So that carbon now has a full octet. Likewise, this carbon over here, if I tally up its total electrons, it's got 1, 2, 3, 4, 5, 6, 7, 8. So both carbons are sort of happy and satisfied. They both have their octet. But we now have this different arrangement of atoms here. This would be written as a carbon-carbon double bond, which in the shorthand sort of line methodology of drawing out would look like this. So we would draw a carbon with 2 lines, and those 2 lines would represent the 2 sets of shared electrons in the double bond. So in terms of the consequence of shape now, going back to our analogy of the central point with a tethered string with charges now, in this case I only have 3 charges, 3 negative areas. Again, look at this carbon. So this hydrogen with its electrons coming through the bond would be sort of 1 negative area. This one would be another. And then this attached group over here would be a 3rd area of negative charge. So if I now let this adopt its ideal geometry, the negative charges separate. This is just going to go to a very planar structure where all of the strings with their negative charges would adopt a very flat planar structure. And that's exactly what the shape of this type of molecule will adopt. The angles between these strings, as you might imagine, going back to your geometry lessons, will be 120 degrees. So these are at the apexes of a triangle. So this type of shape is called a trigonal planar shape. So the bond angles here around all the angles of the carbon would be 120 degrees. And again, the shape of this is called trigonal planar. So all molecules that have carbon-carbon double bonds like these, they're going to have at least that portion of the molecule will have this trigonal planar shape. All right, in this part of the video, let's take a look at how carbons would look when they're bound now to 2 other atoms. So if I were to start out again with our carbon with 4 valence electrons, in order to have it bound only to 2 other things, what I'm going to have to do is sort of rearrange the electrons a little bit like I did in the previous section. So I'm going to actually move 3 of these electrons over here on one side and have one of the hydrogens, or one of the electrons over here. So if I now attach this to a hydrogen, all right, that's going to give me 1 bond there. And my carbon now has 1, 2, 3, 4, 5. So somewhere I'm going to need to come up with another 3 electrons. So if I put another carbon sort of in the same configuration where I have sort of 3 electrons over on one side, 1 over here, now you can see that I would have 2 carbon-hydrogen bonds, one on either side. But now if you look at each of the carbons, I now have a full octet. I've got 6 here, 7, 8. Likewise over here, I would have 6 plus the 2 gives me 8. So notice there's now 3 pairs of shared electrons, and this is called a carbon-carbon triple bond. So we would represent this in the line drawing like this. So we just sort of shorthand those little electrons as just 3 lines. And going back to our analogy of the string, if I had 2 tethered negative charges attached to a central point, and I allowed those to now separate as far as they could, this is just simply going to adopt a very straight linear type of arrangement with an angle now of 180 degrees. This is called a linear arrangement. So molecules that have carbon-carbon triple bonds, the angles between those bonds are going to be 180 degrees. And this is just simply called linear. So molecules that contain carbon-carbon triple bonds like this are going to adopt this shape of being a linear. So just to review, carbon-carbon single bonds adopt a tetrahedral shape, bond angle of 109.5. Carbon-carbon double bonds, they adopt a trigonal planar shape, adopt a bond angle of 120. And then lastly, carbon-carbon triple bonds adopt a linear shape with bond angles of 180. So I hope that helps you visualize a little bit of how carbons can actually adopt these different bond angles.